Okay. Okay, just about time to get going here. Let's see. The other day or yesterday, we actually started talking about Einstein's postulates of special relativity. And he based the whole thing on just a couple of postulates. One was that the laws of physics are the same in all inertial reference frames. And then one that comes up as a consequence of that is that the speed of light is a constant in all reference frames, regardless of the motion of the source or the observer. And so the speed of light kind of depends on the properties of space. And if that's going to be the same for all observers, then something has to give. And today we'll take a look at one of the very first things that gives, and that's the measurement of time. So I'm going to have you imagine a light clock, and I'll just draw a kind of blown up version of one here. And the way this clock will work is that at some point you're going to have a light source, and this light source can just be something like a strobe light that flashes every so often. And then there's going to be a photocell that's over here. And the photocell will register whenever it gets a flash of light, but there's a barrier between the light source, this is the light source, and the photocell. So the light can't go directly from the light source to the photocell. Instead, it has to come up here to some mirror that's way up here, some distance away from it. And so the light travels from the light source and back down to the photocell. And so that'll be the time interval that this clock registers, is the round trip light travel time between the light source and the photocell. And so if you have a distance L that's between the light source and the mirror up there, then the time interval that this thing will register is going to be 2L over C. And this will be delta T is 2L over C. And this is just the distance divided by the speed. and that'll be the time. And we're going to call this a proper time because it's measured in the rest frame of the light clock. And so in relativity, we'll at times be talking about proper times or proper lengths. And it's a proper time if you're in a reference frame where the thing you're talking about is at rest with respect to you. And so this will be a proper time in that case. We'll assume that this distance L can be very large to the actual physical separation between these two things. So this angle is going to be minuscule and not have an effect on what's going on here. And then the way this clock works is that when the photocell gets a light pulse from that reflection, that an electric signal will travel a very short distance through a wire and make the light source trigger again. So then this distance will be minuscule or negligible compared to this distance here. So that'll be the way the light clock works. Now, that's the way it looks in the reference frame of someone who is at rest with respect to the clock. But what if someone sees this clock as a moving object? And so we'll imagine that that's going on here, and we'll put a series of mirrors up here, or actually just 3. So there's one mirror, second mirror. Well, I'm going to save some paper for writing on, but actually it's the same mirror, it's just at different times. And so but it's moving. And then down here we'll have the photocell and the light source. Okay, so light source, and our first event here is going to be the light flash. Light source that is not flashing, photocell that is not receiving. And okay, light source, photocell, light source, photocell. So this will be observations made in the reference frame of someone who sees the clock moving to the right with a speed v. So from viewpoint, seeing clock move to the right at speed c. Whoops, speed v, excuse me. C is the speed of light. And we're going to find out that things can't go that fast except light. So the first event, the light flashes. Okay, second event, the light is received at mirror. So and the third event is going to be the reflected light arrives at the photocell. So now, during the time of these 3 events, this clock is going to have moved to the right. Let's see, I want to extend this thing up here a little bit. And just because I scribbled all over the bottom, I'm not going to be able to do this. But the clock will have moved to the right in this time interval a distance v delta t prime. And delta t prime is going to be the time measured in the reference frame of the person who sees the clock as a moving object. So, and this is going to be an important thing. So sees the clock moving by at speed v. And we'll see how that works out. Well, for one thing, in their reference frame, the light is going to travel from the light source up to the mirror, but it's not going straight up to the mirror. It's going to have to be going at an angle. And then they'll see that light come from the mirror back down to the photo cell, which they'll also see as some angle here. I didn't do the greatest job lining those up, but whoops, it's supposed to come all the way down to here. They'll say it doesn't just have to go up here and down, it has to go sideways some distance as well. And so just right off the bat, they're going to say, your clock's running slow. You only get some particular time interval when I actually get some longer time interval because the light has to go farther. And that's going to be a weird thing, but we can do some math with this and figure out what's going on. Now, both observers, there are some things that they agree on and some things they'll disagree on. One thing they'll agree on is the speed of light. The speed of light is the same for everyone, regardless of the motion of the source or the observer. And another thing they agree on is their relative speed. And so they'll both think that, yes, the clock is moving by at the speed v for one person's observation. The person who's in the reference frame of the clock will say, yes, I see you moving by me at speed v. And so they'll agree on that speed v, get the same number for it. But let's see if we can reconcile or get some sort of a number put on how much they disagree by. And to do that, I'm just going to draw this triangle right here and monkey around with it a bit. Let's see, I'll try to do this here, draw a little right triangle. This side of it is going to be L, and they'll actually agree on that amount L. They'll agree on the measurement of lengths that are perpendicular to the direction of travel. So this is L. Let's see, this is going to be V delta T prime divided by 2. The whole thing is V delta T prime, but half of it is what we're looking at here. And then this up here is the distance that this person who sees the clock as a moving object has to travel. Well, there's going to be a right triangle. This will be the square root of L squared plus V delta T prime over 2 squared. Okay. Now, the total distance that they see this thing traveling is going to be twice this. And so the delta T prime will actually end up being twice the square root of this thing, L squared, because it goes up that far on the one part of the trip and comes back down that part. So L squared plus, I didn't write that very neatly, but V delta T prime over 2 squared. And we divide that by the speed of light. And so that's what we get. Okay, well, we're going to do some algebra with this thing. We're going to try to isolate the delta T prime and solve for it in terms of other things. And so then we can compare that delta T prime to the delta T that we happen to have here and see how those two numbers compare with each other. Okay, well, let's see. I think the first thing I would do is maybe square both sides. And so delta T prime squared is going to equal square this side, and I'll get 4 times L squared plus V delta T prime over 2 squared. And when you square a square root, you just get what's inside of it. The 4 is from the 2 that was in front. And then on the bottom, I've got a C squared here. And let's see, try to isolate this term here. Whoops. This should have been out there. Okay. Delta T prime squared is going to be, let's see, the first part of this will just be 4L squared over C squared. And then I factored the, whoops, plus, excuse me. When I square this, I will get, I'm making this messy, but I'll get V delta T prime squared over 4, but I'm multiplying that by 4. And then I've actually got C squared here on the bottom from that. And that was probably messy algebra, but I'm pretty sure we're okay with it. These 4s will just divide out. And so I'll bring that across and I'll have delta T prime squared plus, this is actually V squared delta T prime squared over C squared, and that will equal 4L squared over C squared. Then factor the delta T prime squared out of here, and I'll get delta T prime squared.
Wait, you subtract the V squared delta T squared first.
Like that?
Yeah.
Yeah, it should have been a minus sign. Okay, anyway, left inside here, I'll have 1 minus V squared over C squared. And then that equals 4L squared over C squared. Okay, divide both sides by this quantity in parentheses here, and I'll get delta T prime squared is equal to 4L squared over C squared divided by 1 minus V squared over C squared. So got that. Now I just take the square root of both sides and I'll have delta T prime. And delta T prime will equal, well, the square root of this thing on top is 2L divided by C. Square root of 4 is 2, square root of L squared is L, and square root of C squared is that. So the top has 2L divided by C, and the bottom is the square root of 1 minus V squared over C squared. Okay, 2L over C is the delta T. That's the proper time that's measured in the reference frame of the person who sees the clock as a moving object. And so I could rewrite this as delta t times 1 over the square root of 1 minus v squared over c squared. And this combination that's in parentheses here shows up again and again in special relativity. And we actually give it its own little letter. It's the Greek letter gamma, shows up, we'll see it a whole lot, but it's going to equal 1 over the square root of 1 minus v squared over c squared. Now, v is going to be less than c. You're always going to have, at least in this calculation, we'll always have a positive number under this square root. We're not going to go with imaginary numbers here. And if v is very small, v over c is going to be a small number as compared to the speed of light. And when you square it, it gets even smaller. For very low speeds, this is going to be approximately 1. And so the moving clock and the rest frame values will be unmeasurable practically, unless you have something like an atomic clock. But much of the time that'll be the case. But at any rate, this simplifies to just delta t prime is equal to gamma delta t. Delta t is the time that passes in the rest frame of the clock. Delta t prime is the time that passes in the rest frame of someone who's seeing the clock as a moving object. And they get a longer time span. They will look at that moving clock and say, your clock is running slow. And so this is one of the fundamental ideas of special relativity. And you often just hear moving clocks run slow. But that's according to, I'll have to get rid of this piece of paper. It was written on too much, but according to, I'll just say observers, who see the clock as a moving object. Whoops, a dying pen. Okay, that one's toast. Moving clocks run slow according to observers who see the clock as a moving object. Okay, I just did a light clock. Seems like something just weird, but at the most fundamental level, every process you can think of will eventually depend on some sort of electrical signal running from one place to another. That's like a light clock. If you imagine some part of the human body where this could be one nerve cell and maybe this is another nerve cell, okay? And in order for one of these nerve cells to transmit information to another one, there will have to be some sort of an electromagnetic signal at a very basic level that travels from one of them to the other. Well, if someone sees this as a moving object, it's not just going to travel that little distance. It may have to travel a longer distance instead of a short one. And if the clock is moving in that direction at some speed that's fairly large. So you get weird things like that happening. Every process is going to run slow according to observers who see the objects as moving objects. So biological processes will run slow. Someone who's moving at a high rate of speed will have a longer life according to someone who's not, who sees them as a moving object. And but it goes both ways. The person who, well, yeah, motion is relative. Everybody thinks everybody else is moving with respect to them, and they don't get that. Now, I want to show you something about just how much of a difference this makes, and I'll drag an Excel file over here. Let's see. This graph doesn't look great, but or the graph that I'll show you doesn't look so great. I guess I could drag the other one over. Here's a calculation of gamma, and I've got, well, I can zoom in on this thing. 0.1. That's actually a pretty high rate of speed. The left column is v over c. It's the fraction of the speed of light that something happens to be moving. And 0.1, that means it's going at 10% or 1/10 of the speed of light. And at 1/10 of the speed of light, the difference is going to be not much. Gamma is equal to 1.005. So what is that? 0.5% difference at 10% the speed of light. So not very noticeable. If you double the speed of light, though, the difference ends up actually getting quite a bit bigger. It's 4 times as big as the difference, but it's going from 0.5% to about 2.1%. And then you start tagging on tenths of the speed of light, 30% the speed of light, or 0.3, 1.048. Okay, that's a 5% difference. 40%, it's up to a 9% difference, and then it starts seeming to accelerate. Something interesting happens. You get to 0.9 for v over c. The difference, gamma, ends up being 2.294, basically 2.3. That's a huge difference, but then you add another 9. So you're adding 0.09 onto it, which is 9% of the speed of light, and the difference triples, more than triples. And add a 5 onto that, well, not so noticeable. But if you go from 0.99 to 0.999, that's adding, let's see, 9/100ths of the speed of light, less than 1% of the speed of light, and it triples again from what it was at 0.99. And every time you add another 9 onto this, you're adding less and less speed, but the difference will triple again. So it'll jump from 22.37 to 70.71, and it just keeps repeating that process. At particle accelerators, they'll get electrons and protons accelerated to 0.999999 times the speed of light, and things behave much differently when that's the case. I made a graph of this, but it's not very smooth because I don't have very many data points, and it looks like kind of a bumpy graph, but it would actually be quite a smooth graph if we filled in the some of the missing spots that are on here. And that's the way gamma behaves. For a long time, it's barely different from 1, which is what the value is on this horizontal stretch down here. And doesn't make a whole lot of difference, but once you get past 80% of the speed of light, or 0.8 for v over c, it starts taking off through the roof. And so where these effects are going to be the most noticeable is in particles that are traveling very close to the speed of light. So most of the examples we're going to look at are going to be dealing with situations like that. And although not always, sometimes we'll consider other things. Special relativity and general relativity both predict things differently. General relativity would make predictions based on the strength of the gravitational field you're in. For special relativity, it's the predictions are based on the relative speed of the two observation frames you're talking about. And however, both effects have to be taken into account when people are using GPS satellites. And if you didn't allow for the relativistic corrections on GPS, the errors would build up over time. And before long, you'd be a few kilometers off in your measurement. And if you're plowing your field using GPS on your tractor, you could be way fouled up and plowing up your neighbor's field instead of yours, something like that. So that's a place that one of the few practical applications of special relativity is in that stuff. Okay, so let's talk about some high energy particles, muons. Okay, muons are an elementary particle that are created in collisions, and
I think you have to switch to the IP vote.
whoops. Okay, actually,
Sorry,
I have
Excel
to.
sheet.
Yeah, I have to drag the Excel file out of the way. Let's see. All right, back to this thing. So they're accelerated to a speed of 0.9994 c. We can make them in particle accelerators. You smack a few things together and you get muons out of it. They're negatively charged. They actually have the same charge as an electron. They're more massive than electrons. And I can't remember if it's 207 times as massive or 270. It's one or the other. But they have a lifetime of 2.2 microseconds in the reference frame of the muon. But what will their lifetimes be as measured in a laboratory frame of reference? Well, this thing is the proper time. We can call that the delta t. The laboratory frame of reference, we can think of that as the delta t prime, and it's going to be gamma delta t. And so we just need to calculate gamma for 0.9994 c, which is easy enough to do. I would just go 1 divided by the square root of 1 minus 0.9994 squared, and I get 28.9. So it would be, let's see, actually I can keep 4 sig figs on this, but I've only got 2 on that lifetime. But I'll go ahead and 2.2 microseconds. And I'd get about, let's see, 64 microseconds is about what I'd get. Okay, now during their lifetime, how far will they travel in the laboratory frame and in the muon frame? Well, in the laboratory frame, we would use this for the time that passes, and we'd use this as the speed for the muons. Everybody will agree on the relative speed of the muons, so we'll get that. So lab frame, the distance that they travel, and well, I'll just call it D lab, I guess. That'll be the delta t prime. It'll be V delta t prime, but V is 0.9994 c, so 0.9994, and it doesn't matter how many sig figs I keep on here. I've only got 2 on this. And then 3.00 times 10 to the 8th meters per second is good enough for that. And then 64 microseconds times 10 to the minus 6 seconds. And that distance in the lab will end up equaling, oh, let's see, if I save that till last, I can just replace it at the tail end. So I think I've got everything I need. Okay, in the laboratory frame, they'd travel a fair distance, actually, 19,000 meters, okay, or 19 kilometers. But, so if you had a, like say a particle accelerator that was a linear particle accelerator where they went in a straight line, you'd have to have it being 19 kilometers long. Otherwise, they're going to run into the end of it and you're going to lose your little muons there. But in the muon frame, okay, the distance for the muons is just going to be how fast they think they're going times 2.2 microseconds. So it'll just be 0.9994 times 3 times 10 to the 8th meters per second times just 2.2 microseconds. Now, well, let's go ahead and calculate it here. Let's see. Yeah, that'll work. Okay, they're only going to get a distance of about 660 meters is how far they think they traveled. Now, here's something. This lab distance is something that someone in the laboratory, they could take a tape measure and they could have one observer who sees where the muons are created. They could have another observer in the lab, have observers strung out along the particle beam or the particle path until they see it decaying. And then somebody could take a tape measure and at their leisure measure the distance between those 2 points. And so this is actually a proper length. However, this length, according to the muons, they're going to see this 19 kilometers of laboratory racing by them at 0.9994 times the speed of light, and they're going to see it as a shorter distance. And they're only going to see 660 meters passing by. So here's another thing that shows up with special relativity. We have that moving clocks run slow according to observers who see those clocks as moving objects. We'll also have that moving lengths appear shortened and a key part is along the direction of motion. And this is according to observers who see the length as a moving object. So the length, slide it up there. Okay, So that's something else that happens. So if you remember those two things, moving objects appear shortened along the direction of motion and moving clocks run slow, between those two, and actually with those kind of offsetting effects, is why people or observers in different reference frames end up agreeing on the relative speed of the two reference frames. The way the formula works out for this one is that the, let's see, grab another. This one doesn't look too bad. For the length thing, if you let L equal the proper length, and this would be the length where you've got the ability to just take a tape measure and measure that length at your leisure, or just take a meter stick, flipping it end over end the whole time. You can measure it that way. So it's at rest with respect to you, whatever the object happens to be. But for someone who's racing past, they don't have the leisure to do that because they have to use clocks and various things to figure out where it is at different times and stuff like that. That would be a moving length, and the L prime ends up equaling L divided by gamma. And so you divide by that thing that's always bigger than 1, and the faster the two objects are moving with respect to each other, the bigger the value of gamma. In fact, gamma in this case was actually, what did we figure it out? 28.87. That's a pretty large value for it. Now, here's the thing about muons. They're generated high in the atmosphere, and they're generated by cosmic rays that are coming into the Earth's atmosphere. And cosmic rays are mostly electrons and protons, but when they strike particles in the upper atmosphere, the nuclei in the upper atmosphere actually, they will produce these muons. So they're generally generated pretty high up there. You've actually got, I think I heard a talk by a particle physicist one time, and they said, you've got 2 muons going through your head every second. Okay, so that's a cheery thought, but they don't interact that commonly. And so they, over your whole lifetime, you might have one of those muons actually doing something to interfere with your body. And so the odds aren't bad that you're going to be affected by those things. However, if you spent a lot of time in space, you'd have a lot worse things going through your head all the time. So don't want to mess with that. Most muons get absorbed by the, or many of them get absorbed by the atmosphere, although I want to show you something that happens. And let's just suppose that there was no time dilation and we still had muons being generated 100,000 or 30,000 meters up in the atmosphere. And this will be where the muons are created. Okay. Now, if you fly a balloon up to 30,000 meters, which is doable, a lot of study balloons, research balloons get floated higher than that by quite a bit. And oh, I can't remember how many years ago it was now, but when Felix Baumgartner jumped out of that balloon, I think he was about 40,000 meters up actually when he jumped out and did that thing. And then the following summer, somebody went even higher than he did, but they didn't televise theirs. Anyway, they're created up there. Now, in the reference frame of the muon, they travel almost the speed of light, and every 660 meters, when they refer to that as being their lifetime, by the way, that 2.2 microseconds, that's actually an average lifetime. It's like the half-life is what it is. every 2.2 microseconds, half of the muons would decay. So if there wasn't any relativity going on, by the time you'd get down 660 meters below that level where they're created, half of the muons would decay. And every time you go another 660 meters, half of the muons would decay, and so forth, with that lifetime of 2.2 microseconds. And by the time you've gone 30,000 meters down, you've got a lot of 660 meter distances folded into that. So if we take 30,000 and divide by 660, you've got about 45 halvings that would occur. And if you take 1/2 to the 45th power, and this is just approximate, but 1/2 to the 45th, you'd get about 2.8 times 10 to the minus 14th. That would be the fraction of the muons that you had up here that would show up down here at the surface, okay? Well, that's hardly any. And so whatever number you were getting up here, you're going to be getting essentially 0 down here. When you multiply it by 2.8 times 10 to the minus 14th, that's not going to show up in your detectors anymore, except rarely. But that's not what happens. What we have happening is that the muons that are created up there, we have almost as many down here on the Earth's surface. And the reason for that is their lifetime gets extended. And so let's see, wherever I put that thing, there we go. Instead of a 2.2 microsecond lifetime, they've got a 64 microsecond lifetime, according to us. And if you take that, 64, oh, well, we figured it out. 19,000 meters. And so, well, this is only 30,000 meters. So you'd be most of the way to the ground before half of the muons have decayed. And then you'd have another partial diminishment here. But you get comparable or numbers down here at the ground level in a muon detector that are a little less than half as high as what you would have had up here. And so you don't have 45 halvings of the numbers of muons. You've got them still a reasonably high number, only a little less than half of what you would have up here, but still pretty high numbers. So that's something that happens. And that was one of the first observational verifications of this effect, which we call time dilation, that moving clocks run slow. Okay, well, let's think about that length contraction bit. That's what the other thing is called. The rest radius of the Earth is 6,370 kilometers, and its orbital speed around the sun is 2.98 times 10 to the 4th meters per second. By how much would Earth's diameter appear to be shortened to an observer positioned so as to be able to watch the Earth move by at that speed? So the Earth is usually this nice spherical thing here. And okay, it's got a radius of those 6,370 kilometers. And so the diameter is going to be twice that, which is 12,740 kilometers, approximately. But it's moving through space around the sun at its orbital velocity, v orb, of 2.98 times 10 to the 4th. How much is it going to be shrunk by? Well, let's see. We may have to do an approximation on this thing to be able to figure this out. We've got its ordinary diameter, and I'll just put a D on that thing, and it's going to equal twice this thing. So 12,740 kilometers. Okay, well, let's see. The d prime is going to be that number divided by gamma. So let's see what gamma happens to be for this thing and what my calculator will tell me it is. It'd be, oh, show you something that I haven't brought up yet. V over C is often given a shorthand notation of just the Greek letter beta. And in special relativity, beta is just going to stand for that particular calculation. It's the fraction of the speed of light that something is going. Well, in this case, if I take the 2.98 times 10 to the fourth and divide by 3.00 times 10 to the eighth, and I know I don't have to input the 0.00 into my calculator. I would get about, in this case, 9.93 times 10 to the minus fifth. And when you use this beta as the abbreviation for V over C, gamma then ends up being 1 over the square root of 1 minus beta squared. And so we can see how that's going to work out here. In this case, 1 divided by that square root of 1 minus that last thing I used, my answer squared. I get to 4 significant figures, 1.000. And let me show some more significant figures in here. I can go to my mode and show 9 digits after the decimal point. And if I multiply that last number by 1, okay, I get 1.0, a whole bunch of zeros, and then I finally get a 5 showing up. All right, well, I only know the diameter to 4 significant figures. It's not going to be noticeable, okay? However, all is not lost. What I can do is calculate the difference between this diameter and this diameter. And I'll show you how I do that. And this will be the last thing that I set up here today. I won't finish the calculation, but instead, the question actually asked, by how much would the Earth's diameter appear to be shortened to an observer positioned so as to watch it move past? So it's actually asking d minus d prime, which is equal to d minus d divided by gamma, which is the diameter times 1 minus 1 over gamma, which, let's see, well, maybe I can do something with 1 over gamma. 1 over gamma, since gamma is 1 over the square root of 1 minus beta squared, 1 over gamma is just going to be that square root. So okay, well, I'm going to use a little something called a series expansion. Beta is going to be a very small number in this case. And here's the series expansion I'm going to use. This is for this power series, can work out pretty well here. 1 plus x to the n, I'll write it bigger here because it's probably too small to see, is equal to 1 plus nx plus n times n minus 1 times x squared over 2 factorial. And then you keep going. The next term has x cubed. The one after that is going to have x to the fourth and so forth. Well, our x is going to be minus beta squared. Our n, in this case, is going to be 1/2. We're raising this whole thing to the 1/2 power. So I can think of this as 1 plus minus beta squared to the 1/2. Now, some of you are in third quarter calculus, and you probably spent a bunch of time this quarter dealing with sequences and series. I don't know if you would have seen this power series or not, but this one works, and it works especially well when x has a small value. Think about that first term. It's going to be 1/2 times minus beta squared. Okay, that's going to be a pretty small number. Let's see. Yeah, and it'll also end up having a minus sign on it, is what it is. So it'll be 1 minus 1/2 beta squared. The next term is going to be beta squared. Well, beta in this case is 10 times 10 to the minus 5th, which is about 10 to the minus 4th. Okay, when you square it, you're going to get 10 to the minus 8th. And so this is going to be 1/10,000th the magnitude of that. And the next one is going to be, when you cube it, you're going to get about 10 to the minus 12th. So that'll be 1/100 millionth the size of this. So we can actually ignore everything beyond this term. And the reason I'm not going to ignore this one is because I want 1 minus 1 over gamma. And so what I'll get here is 1 minus just the first two terms in this expansion, 1 minus 1/2 beta squared is what I get for that thing, which ends up being the diameter times when I distribute that through there, I get 1/2 beta squared. So I approximated the 1 over gamma with just 1 minus 1/2 beta squared. And if I included the next term, it's not going to be enough to matter, but this is enough to try and figure it out. So the beta squared ends up being pretty tiny, but anyway, I can multiply that by the diameter of the Earth and get an idea that'll be good to, let's see, I only had 3 sig figs on beta, so that's all I can keep on there. But I'll be able to keep 3 significant figures, and it may be some number of millimeters, it might be some number of micrometers, but it'll still tell me how much the Earth's diameter is shrunk by. It's not going to be much, but I could still calculate that. So try playing around with that over the weekend, and we can start from there on Monday. And we'll be working on this same batch of handouts that I've got posted for today on Monday. We're going to continue moving on with those things. And we will use this series expansion several times during the quarter or during this last couple of weeks. And it's kind of a fun one to use. And it's probably your first example of using something like this. So I'll try to stress it whenever we do it. Okay, we'll stop there. I'll be putting up a homework assignment, our first homework assignment on special relativity. And we might have 2 on this in this last couple of weeks. So turn you loose there. Let's see, what am I doing? Stop the share. Okay, any questions on that? Well, have good weekends.